Deep Learning Part 6, Training Deep Networks. We have the full engine now, forward loss, backward update. But a network that scores perfectly on its training data can still fail completely in the real world. This part is about the gap between memorizing and truly learning, and how to close it. First, the real goal, and it is subtle. It is not to memorize the training set. Any large enough network can do that perfectly. The goal is generalization, performing well on data the network has never seen. Low training loss is easy and almost meaningless on its own. Low error on new examples, that is the entire point of learning. So we never ever trust the training loss alone. Instead, we split our data 3 ways. A training set to fit the weights. A validation set to tune our choices and watch for trouble. And a test set locked away and touched only once at the very end. The test set is the honest, final judge of how well we truly did. Now the central danger of all machine learning, overfitting. Watch these 2 curves. The training loss keeps falling happily toward 0. But the validation loss falls, then turns and begins to climb. At that turning point, the network stopped learning the true pattern and started memorizing the noise. That growing gap between the curves is overfitting made visible. The opposite failure is underfitting. Here both curves stay high and flat. The model is simply too simple or trained too briefly to capture the pattern at all. Underfitting wastes the model's capacity, overfitting wastes its ability to generalize. And the art of training is finding the sweet spot right between the two. That balance has a classic name, the bias-variance tradeoff. A model too simple has high bias. It misses the truth systematically no matter the data. A model too flexible has high variance. It swings wildly, chasing the noise in every sample. Total error is the sum of both. And the best generalization sits at their minimum between them. You can feel this by sweeping the model's capacity. Too little and the fit is crude, error high. Add capacity and the fit improves, error falls. But push too far and the model starts memorizing, and the error on new data climbs back up. The classic error curve is a U, and we aim for the bottom of that U. The tools that push us toward that bottom are called regularization. And they all share one simple idea. Among all the ways to fit the training data, gently prefer the simpler ones. Because simpler solutions tend to generalize. There are several ways to nudge a network toward simplicity. Let us walk through them. The first is weight decay. Add a penalty to the loss for large weights, the sum of their squares. Now the network must justify every large weight by reducing the error more than the penalty costs. So it settles on smaller, smoother weights. And a smoother function is a simpler one, which generalizes better. The second is beautifully strange, dropout. During training on every single step, randomly switch off half the neurons. The network can never rely on any one unit, so it must spread its knowledge across many. It is like training a huge ensemble of smaller networks all at once. And at test time, every neuron returns and they vote together. The third attacks the problem at its very source, data augmentation. Take each training example and transform it in ways that do not change its meaning. Flip an image, rotate it, shift its colors slightly. Suddenly, one photo becomes many. And more effective varied data leaves the network far less room to simply memorize. The fourth is the simplest of all, early stopping. Watch the validation loss as training runs. The moment it stops falling and begins to rise, stop. And keep the weights from that very best point. You halt exactly where generalization was strongest just before overfitting sets in, free and remarkably effective. And the most powerful regularizer of all is not a trick at all. It is simply more data. The more genuine examples a network sees, the harder it becomes to memorize them, and the more it is forced to learn the real underlying pattern. When you possibly can collect more data, nothing else comes close. Before training even begins, one choice matters more than it first appears: how to set the initial weights. Too large and the signals explode or saturate at the very first step. Too small and they fade to nothing as they cross the layers. Principled schemes scale the initial weights to each layer size, keeping the signal steady from top to bottom. Even with good initialization, the activations drift as training changes the weights. Batch normalization fixes this in the middle of the network. At each layer, it recenters and rescales the activations using the statistics of the current batch. The result: faster training, higher safe learning rates, and a smoother, gentler loss landscape. A close relative normalizes across the features of a single example instead of across the batch. This is layer normalization. It does not depend on the batch size at all, and it works cleanly on sequences of any length. For those reasons, it is the normalization of choice inside the transformer, which we reach in Part 8. Among all the knobs, one dominates them all: the learning rate. Get it wrong, and no amount of regularization will save you. Too high and training diverges, too low and it crawls for an eternity. Find a good value, then decay it over time. If you tune only one thing in your entire network, tune this. The batch size matters too. Small batches give noisy but frequent updates, and that noise adds a helpful regularizing jitter. Large batches give smooth, stable gradients, and they use the hardware more fully. It is a trade between noise and speed, and it interacts closely with the learning rate, another dial to balance. All these choices, the learning rate, the regularization strength, the architecture itself, are called hyperparameters. And crucially, we do not learn them by gradient descent. We search for them. Train a network, check the validation loss, adjust, and repeat. Much of practical deep learning is exactly this: a patient outer loop of tuning. One more reliable trick: ensembling. Train several networks independently, perhaps from different starting points. Then average their predictions. Their individual mistakes are often uncorrelated, so they cancel out, and what remains is the signal they agree on. An ensemble almost always beats any single model within it. Here is the good news: the curves tell you exactly what to do next. A large gap between training and validation: you are overfitting. Add regularization or more data. Both losses stuck high: you are underfitting. Add capacity or train longer. Read the two curves, and the next move is almost always clear. So here is a sane recipe for training almost anything. Start simple and get the network training at all. Then scale it up deliberately until it overfits, because that proves it has enough capacity. Then and only then regularize and add data until the validation loss is as low as you can push it. Overfit first, then tame it. One modern surprise worth knowing. The classic wisdom says bigger models eventually overfit and get worse. But push very large models far past that point and something strange happens. The test error falls again. This is called double descent. It is part of why enormous models defy the old intuitions and simply keep improving. Which points at the deepest lesson of the last decade. For many problems, the most reliable way to do better is not a clever trick. It is more data, a larger model, and more compute. The techniques in this video keep that scaling stable and healthy. But the scaling itself has been the engine of progress. We can now train a solid general network on almost any data. Forward loss, backward update, kept honest by regularization. But so far our networks treat their input as a flat, unstructured list of numbers. For an image that throws away almost everything that matters. The grid, the shapes, the locality. So part 6 in one line. Training deep networks is the art of generalization. Fit the pattern, not the noise. We can now train well on almost anything. Next, we specialize the architecture to the structure of images. Part 7, Convolutional Networks.